Hey guys, what's up? Today we're looking at doing some more operational properties for Laplace transforms. And last time, just to recap what we did last time, we did the first translation theorem. So that was Laplace of e to the at f of t equals f of s minus a. So that was the first translation theorem. And then we had the second translation theorem, two parts. And that said Laplace of u of t minus a times f of t minus a equals e to the negative as f of s. And really that one's better to write as an inverse on the right and then the function and the unit step on the left. And then we had Laplace of u of t minus a times f of t equals, or even we could say g of t. Let's call it g of t instead of f of t right there. Call it g. This is equal to e to the negative as times Laplace of g of t plus a. And we said one of those forms for the Laplace second translation theorem, one of the forms was better to go from t to s, and that's the second form. And then the other one, the first one, is better to go from s to t. So this is to go from s to t, whereas this one's to go from t to s. And then, let's see, did those translation theorems, and then we did transform of a derivative, derivative of a transform, which was Laplace of t to the n f of t equals negative 1 to the nth derivative with respect to s of f of s. So those are the operational properties we covered last time. So this is all from last time. So today what we're looking at is some more of these types of properties, and what we can do, solve some different types of equations, and then also we're going to look at periodic functions and try to get into the Dirac Delta function before we end off today. So we've talked about derivatives of transforms and transforms of derivatives. Today we're going to look at transforms of integrals. So the first thing today is going to be transforms of integrals. Transforms of integrals. So that's going to be the first thing today, and we define something called the convolution. So definition, the convolution of f with g is defined by f star g equals integral from 0 to t f of tau g of t minus tau d tau. So it's just an integral, this convolution thing. It's just an integral. And I want to make a note of a couple of things here. This star means convolution, not multiplication. It means convolution. So if you write a star, I assume you're talking about convolution. So that's pretty important. Don't mix up that notation with like multiplication. It's a convolution. All right, so that's f star g, and it turns out that f star g is equal to g star f, so theorem. f star g is equal to g star f. What would g star f be? G star f would equal the integral from 0 to t g of tau f of t minus tau d tau. So it doesn't matter which one you write first, and actually we could show this by u substitution. So proof here, f star g is equal to integral from 0 to t f of tau g of t minus tau d tau, and I'll let u equal t minus tau, and then du equals negative d tau. And if tau equals 0, u equals t, and if tau equals t, u equals 0. So this becomes integral from t to 0 f of t minus u g of u negative du, which is integral from 0 to t g of u f of t minus u du, which is g star f. So this convolution thing is what we call symmetric. So this means convolution is symmetric. Some people might say commutative. So any questions so far? It's just a way to multiply two functions and then integrate them. So that's what this convolution thing is. It's like an integral of two functions multiplied together in a certain way and integrating them in a special way. So any questions? All right, so the convolution theorem tells us how to take Laplace transform of this convolution thing. So convolution theorem. Convolution theorem says Laplace of f star g is equal to Laplace of f of t times Laplace of g of t. And if we're used to capital letters to represent the Laplace transforms, we could just say f of s times g of s. And likewise, we could say Laplace inverse of something like f of s times g of s be equal to f star g, where Laplace inverse of f of s equals f of t, and Laplace inverse of g of s equals g of t. So that is the convolution theorem. either way you want to write it. You can say going from t to s like this, or you can say going from s to t like this. Either one you could call the convolution theorem. So it just basically tells you how to take the Laplace transform of this integral, f star g, or g star f. All right. Example. Find Laplace transform of e to the 2t sine t, or star sine t. Alternatively, that could be asked. So alternate question could be find Laplace transform of integral 0 to t e to the 2 tau sine of t minus tau d tau. So that could be another way this question could be asked, if that makes sense. So I just told you that it was a convolution directly in the question, you know, right here with the star, but it could be given like in the explicit integral formulation, and then you'd have to recognize that that's a convolution. So here you would need to recognize this is a convolution. So yeah, good stuff. Questions so far? Solution here. Well, Laplace of a convolution e to the 2t star sine of t is really just Laplace of e to the 2t times Laplace of sine t. And that gives me 1 over s minus 2 times 1 over s squared plus 1. And that would be our Laplace transform for this integral, e to the 2t star sine t. It's pretty straightforward actually when it's given like this. Just multiply the two Laplace transforms together. So it's really not too bad. It's another example. I might say something like find Laplace transform of integral 0 to t tau sine tau d tau So find the Laplace transform of this integral. Well, here it's like I only have an f and I don't have a g. So solution, we see f of t, or f of tau we should say, is tau sine tau which is equivalent to saying f of t is t sine t. But what's g? I don't see g anywhere. I don't see a t minus tau anywhere. So anybody want to take a guess at what g of t minus tau is equal to? So g of t minus tau equals 1, that's right. Which would mean that g of t would also be 1, because if I shift it, nothing's going to change. So that's right, g of t is really just 1. So I've got g of t is 1. F of t is t sine t. So then that tells us the Laplace transform of this integral from 0 to t, tau sine tau d tau, can be written as Laplace of t sine t times Laplace of 1. Very good. So, what's Laplace of t sine t? Well, we have to use the t to the first power. So it's going to be negative 1 to the first power d by ds of 1 over s squared plus 1. Laplace of 1 is just 1 over s. Taking that derivative, multiplying by negative 1, and simplifying, I'm going to skip some steps and just make this 2 over s squared plus 1 squared. After you simplify everything, this is what you'll get. So take the derivative of this function in the bracket, and then multiply by 1 over s, and then multiply by negative 1, and we'll all reduce down to 2 over s squared plus 1 squared. So that is the Laplace transform of this integral 0 to t tau sine tau d tau. So now we have a way to take transforms of integrals. And actually this is a very special case that we want to highlight in general. So in general, Laplace transform of some integral 0 to t f of tau d tau, always you have g of t equals 1. So that tells us that the Laplace integral 0 to t f of tau d tau is going to equal f of s times 1 over s. So that's a nice trick, I guess you could say. It's a nice trick to remember. So, furthermore, you could write it as an inverse transform and say that Laplace inverse of something like f of s times 1 over s would just go back to this integral 0 to t little f of tau d tau. So if you were to evaluate this Laplace inverse, you would just have to do this integral on the right hand side. For example, we won't do this one specifically, but we'll do convolution theorem in reverse. So example, find Laplace inverse of 1 over s cubed times s minus 1. So I'll identify f of s to be 1 over s cubed, and g of s, I'll identify that as 1 over s minus 1. Now, I could use partial fractions. We could use partial fractions to do this, but we're going to use convolution theorem instead. So we'll use convolution, not partial fractions. So we use convolution theorem instead. So what is f of t? What function do I take the transform of to get 1 over s cubed? If you recall, Laplace of t to the n is equal to n factorial over s to the n plus 1. So basically here, n plus 1 is equal to 3. So n was 2. So normally I would have a 2 up there, but I don't. So I put a 1/2 t squared. So that's my function f of t. And my function g of t, if I take the inverse transform, it's going to be e to the t. And now I need to star those. So now Laplace inverse of f of s times g of s is equal to f star g, which is integral from 0 to t, 1/2 tau squared, e to the t minus tau d tau. Now pause, see if there are any questions. All right, so what can we do here? We can pull the 1/2 out of the integral. We can pull e to the t out of the integral. And so this becomes 1/2 e to the t integral 0 to t tau squared e to the negative tau d tau. And how do we integrate this? Somebody help me out. How do we integrate this? Tau squared e to the negative tau. Anybody take a shot in the dark? Do integration by parts. So u dv, put the tau squared here, put the e to the negative tau here, 2t or 2 tau to 0, negative e to the negative tau, e to the negative tau, negative e to the negative tau. And then diagonally, plus, minus, plus. So this integral becomes 1/2 e to the t, that stays the same, multiplied by, see, this can be negative tau squared e to the negative tau minus 2 tau e to the negative tau minus 2 e to the negative tau from 0 to t. So you have a question. It says, if we swapped the g and the f originally, that's right. We would basically, in this integral, so what would happen? Good question. If we were to swap the f and the g right here, then this right here, the tau squared would become t minus tau squared, and this would become e to the tau. And this would become t minus tau squared. So you just kind of like pick your poison, like which function would you prefer to have t minus tau in it? I'd prefer the exponential so I can break it up and pull the e to the t out like we did right here. So that's just a personal preference, to be honest. It really doesn't matter because you could FOIL that thing out, t minus tau squared, and multiply by e to the tau. But I would just, I guess, personally prefer to have the e to the t come out because the tau squared e to negative tau integral seems a little easier to me. So it's just having a little intuition and foresight of what you're going to have to do, but it doesn't really matter, to be honest. But yeah, that's what it would look like if you were to swap the g and the f. Now let's plug in our bounds. That'll give us 1/2 e to the t. And let's see, that would be 0 because tau is getting, or that would be a t, sorry. Negative t squared e to the negative t minus 2t e to the negative t minus 2 e to the negative t. Minus minus would be plus 0 plus 0 plus 2 e to the 0. And that reduces to 1/2 e to the t times, well, I can distribute that all stuff. Let me distribute everything now. This will be 1/2, so negative t squared basically. And then negative t, and then negative 1 plus e to the t. If I distributed that correctly, I feel like I did. Negative 1/2 t squared minus t minus 1 plus e to the t. That is the function we must have taken the Laplace transform of to get 1 over s cubed times s minus 1. Okay, I see the the typo. It's all good. Yeah, that's a good example right there. Good example. Questions? Good question. Good stuff. Other questions before we get going? Keep moving on. Let's see. Example. Actually, we need to talk about something called the Volterra integral equation. that is an equation of the form f of t equals g of t plus integral 0 to t f of tau h of t minus tau d tau. So you have quite a bit going on in this integral equation, and usually the goal is to solve for solve for f. And usually we're given g and h of t and asked to find f of t. So it's like a differential equation, except it's an integral equation. So you could have, you have to find the function f that satisfies this equation, just like you would for like a differential equation, except this has an integral in it. I mean, there could be derivatives in there too. It could be like y prime equals g plus integral 0 to t y, and then some function d tau. So it could be like you have an integral differential equation, but this is just an integral equation. There's no differentials in it. So, yeah, this is called the Volterra integral equation. So let's look at an example of trying to solve one of these equations. So example, use Laplace transform to solve. So use Laplace transform to solve. And the integral equation is f of t plus integral 0 to t f of tau t minus tau d tau equals t. So this is our integral equation. And we're trying to solve for f, basically. So solve for f of t. All right, well, this is really f of t plus f star some function equals t. What is the function that we're starring with? What's the convolution function? G of t equals what? Somebody help me out. So if I'm doing g of t minus tau and I get t minus tau, then g of t would equal t, that's right. So f star t right here. So then now take Laplace of the whole equation. So now take Laplace of both sides. So that'll be Laplace of f of t plus Laplace of f star t equals Laplace of t. And Laplace of f of t is just f of s. F of s times 1 over s squared equals 1 over s squared. If I use the convolution theorem to take Laplace transform of f star t, it's just Laplace of f, which is capital F of s, and Laplace of t, which is 1 over s squared. Now, factor out f of s on the left, so capital F of s times 1 plus 1 over s squared equals 1 over s squared. What I'm going to do is go ahead and multiply by s squared on both sides. Capital F of s times s squared plus 1 equals 1. And so capital F of s is actually just 1 over s squared plus 1. What does that mean capital F of s is equal to? Capital F of s equals what? Oh, sorry. Inverse Laplace. So f of t equals inverse Laplace of 1 over s squared plus 1. And what's that? Inverse Laplace transform of 1 over s squared plus 1. What's that function? What function's Laplace transform is 1 over s squared plus 1? Sine t is correct, so sine t. So f of t equals sine t. Very good. There you go. We solved that integral equation. We found the function that satisfies that equation. One note I want to make here is that integral equation could also have y prime or y double prime in it, like y prime plus integral y times t minus tau d tau equals, I don't know, something like t squared or something like that. So you could have an integral differential equation. So sometimes people call these integral differential equations. So that's like one more layer of like Laplace transform things you have to plug into the equation when you take Laplace transform. But yeah, that could happen. I'd recommend just looking up some book problems just in case. But yeah, that's something else that could happen. All right, good stuff. Good stuff. Last thing for this section is the transform of a periodic function. So transforms are the transform of a periodic function. You might say, well, I already know that. I already know like sine and cosine. Well, what if it's not just like sine or cosine? You know, it's just any arbitrary function f of t plus capital T equals f of t. And capital T is called the period. Sure, sine and cosines are special examples of periodic functions, but there are other periodic functions. You know, you could have like a sawtooth function. Like it's a straight line and then it starts over. Or it could be like a triangular wave, which we'll do in just a second. It doesn't have to just be sine or cosine. Then the transform is given by this theorem, which says Laplace of the periodic function f of t equals 1 over 1 minus e to the negative st, capital T, integral from 0 to capital T, e to the negative st f of t dt. So the only real thing that changes when you have a periodic function is this weird multiplication out front. So that's the only new thing, to be honest. And you don't integrate from 0 to infinity, you just stop at capital T now. So we stop the integral at capital T. So just have to do a integration from 0 to capital T instead of 0 to infinity. So, example. Find the Laplace transform. Find the Laplace transform of f of t equal to, it's piecewise, it's t, 2 minus t, and the interval where it's t is from 0 to 1, and from 1 to 2, it's 2 minus t. And f of t plus 2 equals f of t. So that means the period is 2. So what does this function look like? So let's say this is 1, this is 2, this is 3, this is 4, 5, 6. And this is 1, 2. So what does this function look like? Well, from 0 to 1, it's y equals t, so it looks like this, straight line, if I can get this thing to go straight. And then 2 minus t would actually come down like this, and then start right there. So, and then it repeats. And then that's the periodic part. So it's actually a triangular wave. So the solution, and of course it keeps going. So the solution is really identify the period. The period is capital T equals 2. So Laplace of f is going to be integral from 0 to 2. Whoops, I forgot my multiplier out front. 1 over 1 minus e to the negative 2s. Integral from 0 to 2 f of t e to the negative st dt. But my integral changes on the interval 0 to 1 and then 1 to 2. So this is going to be 1 over 1 minus e to the negative 2s times integral 0 to 1 t e to the negative st dt plus integral 1 to 2 2 minus t e to the negative st dt. And now both of those integrals have to be done using integration by parts. So t e to the negative st 1 0 negative 1 over s e to the negative st 1 over s squared e to the negative st plus minus, and then same thing here, 2 minus t e to the negative st negative 1 0 negative 1 over s e to the negative st 1 over s squared e to the negative st plus minus. So it's going to get a little nasty, but it's okay. 1 over 1 minus e to the negative 2s times, it's going to be negative t over s e to the negative st minus 1 over s squared e to the negative st from 0 to 1. And then minus 2 minus t over s e to the negative st. Minus minus is actually plus 1 over s squared e to the negative st from 1 to 2. All right, that's integration by parts for each of those integrals, and just plugging in the bounds and simplifying, I'll skip those steps. So after simplification, we'll get 1 over 1 minus e to the negative 2s times 1 plus e to the negative 2s minus 2 e to the negative s over s squared. If we combine it all into a common denominator, we'll get this answer. So that's it. That's our Laplace transform of this periodic function. Pretty nasty. But, you know, sometimes you just got to roll with it. Just got to roll with it. Any questions? We'll take a little break, just a minute or so, a couple of minutes. Any questions? That way everybody can catch up. Cool. All right, seems like everybody's pretty quiet today. Not many questions, so we're just going to move on, I guess, to the next section, Dirac Delta function, and taking Laplace transforms with Dirac Delta functions. So we should be able to finish this section, so we'll be done with chapter 7 after today. So moving on to chapter 8, starting next week. So I think we have 3 full weeks left after this week. So next week we'll do, I think we have an exam coming up. So we'll get through some of chapter 8 and then starting chapter 8 after that. We'll see. We'll see how we go. See what we can do. 7.5 is about the Dirac Delta function. So the Dirac Delta function. And this is really just for modeling stuff like impulses, like instantaneously something happens and then stops. So it's like a hammer hits something, or like a golf club hits a ball. It's very it's an impulse. It happens a very short amount of time, but a very large function value. So that's basically what the Dirac Delta function is going to allow us to model. So maybe you inject some stimulus very quickly, and that's it. So definition. We define this function called delta sub a of t minus t0 to be equal to 0 if t is between 0 and t0 minus a, 1 over 2a if t is between t0 minus a and t0 plus a, and then 0 again if t is greater or equal to t0 plus a. And a is usually going to be really small. So if we graph this function, say this is t0, this is t0 plus a, and this is t0 minus a, and then this is 1 over 2a. This is our Dirac, well, this isn't the Dirac delta function, this is just a special function we call delta a. Dirac delta will be a limit as a goes to 0 of this thing right here. So that is called the unit impulse function because the area under this curve is area 1. So we call this a unit impulse function. So the area here equals 1 for all a. Right, this distance is 2 times a from here to here. This height is 1 over 2 times a, so multiplying those we get 1. So the area under the unit impulse function is 1. If we shrink the area, or if we shrink a, so as a goes to 0, we see the function get taller and taller and taller. So let's plot, different values of a. It's really low a. So maybe a is, a is like 1, and then a different a value. Could do a is 1/2. And then maybe we could do a is 1/4. So as a gets really small, then the function gets really tall, but the area is always 1. So the area under the, area under the curve is always 1. So now what we do is we take the limit as a goes to 0 and we define what we call the Dirac delta function. So definition. The Dirac delta function is defined by delta of t minus t0 equals the limit as a goes to 0 delta sub a of t minus t0. And it has the following properties. Number one is that delta of t minus t0 can be thought of as a piecewise function, where the function value is infinity if t equals t0, and 0 if t is not equal to t0. And number two, integral from 0 to infinity delta t minus t0 dt is equal to 1. So the integral of the Dirac Delta function is 1, even though you could think of it as having like an infinite function value at t0. It's 0 everywhere else. So that's interesting. Very interesting function, the Dirac Delta function. And what we're used to, or we're interested in doing, is using it in our differential equations. Maybe your non-homogeneous part is a Dirac Delta function. So your forcing function is just like an impulse, bam, happens at one instant, and then that stimulus is gone from your differential equation. How does that affect your solution to your differential equation? So that's where we're going with this. But before we get there, we need its Laplace transform. So theorem. The Laplace transform of the Dirac Delta function is Laplace of delta t minus t0 equals e to the negative s t0. And this should be saying for t0 greater than 0, greater or equal to 0. And then just a quick note that if that is the case, then Laplace of delta of t would be 1. Basically, that would be when t0 equals 0. So there is indeed a function whose Laplace transform is just 1, and it is the Dirac Delta function delta t. It's like at 0, the stimulus happens, the impulse happens, and then nothing else. And that Laplace transform is 1. So good stuff, good stuff. Examples. Find the Laplace transform of the first one, delta t minus 2, and the second one, delta of, delta of t minus 4 pi. So find Laplace transform delta t minus 2, and then delta t minus 4 pi. So part A, Laplace of delta t minus 2. Well, it's really t0 equals 2, so that's going to be e to the negative 2s. And then part B, Laplace of delta of t minus 4 pi. That's really just t0 equals 4 pi, so that's going to be e to the negative 4 pi s. So not too complicated there, it's just straightforward computation. Substitution t0 into the formula. So any questions so far? All right, now I've got about 3 examples of differential equations, initial value problems. And I think I want to go through all 3 of them just to give you a broad range of examples with these Dirac Delta forcing functions. So let's look at these 3 initial value problems. Example. Any questions before we move on to the initial value problem stuff? Okay, let's look at 3 different initial value problems. So example, solve the IVP. And the first one is going to be y prime plus y equals delta of t minus 1. And the initial condition y of 0 is 2. So solve this initial value problem. So it's like it's technically like a homogeneous equation until t equals 1, and then that impulse happens, and then it goes away, and then it's homogeneous again. So it's kind of like how do you handle a differential equation like that? Like the forcing function is just like at one instant, at t equals 1, something happens very quickly, and then it's gone. So that's our forcing function that we're going to have in this problem. So solution, everything's the same, right? Like we just take the Laplace of the whole equation. So take Laplace of the left, which is y prime plus y, equals Laplace of delta t minus 1. So that's going to be s times capital Y of s minus y of 0 plus y of s equals e to the negative s. And now that can be factored on the left. Y of s comes out times s plus 1 equals e to the negative s plus 2. If I move that 2 over to the right hand side, the y0 is just 2. And now divide both sides by s plus 1, so we get y of s equals 1 over s plus 1 e to the negative s plus 2 over s plus 1. And now take the inverse transform to get y of t. Well, the first part has an e to the negative s, so I know that's going to go back to u of t minus 1. And normally this would go back to e to the negative t, but I can't just put negative t, I have to put negative and then parentheses t minus 1 because it's multiplied by that e to the negative s. So basically that's second translation theorem in reverse. Plus 2e to the negative t. So indeed, we do have a part of our solution which is transient. It goes to 0. So at t equals 1. So this transient term starts at t equals 1 and then dies off. So transient. Transient term pops in at t equals 1, then dies off. And then here's our steady state term. That's always there, all the way out to infinity. And it's actually transient itself. It's actually not steady state, so actually this is also transient. There's no steady state. The steady state is 0. So this is a transient term. From the beginning. So as we expect, something in our solution pops up at t equals 1 and then dies off, in addition to the term that started at t equals 0, which is already dying off. So it's like it was dying off and then it gets reintroduced. Some term gets reintroduced or introduced at t equals 1 and then dies off. So that is that's our solution. We just had to use the second translation theorem in reverse. Just make a note of that, second translation theorem. In reverse. So we had to use the first form of that. Second translation theorem. All right, let's look at another example. This is the solve the IVP, and it's the problem y double prime plus y equals delta of t minus 2 pi plus delta of t minus 4 pi. Initial conditions are y of 0 equals 1 and y prime of 0 equals 0. All right, let's look at this initial value problem. Pretty much the same process. We just have to be careful when we're taking all this inverse transform stuff. That's really the hardest part, is doing the inverse transform, partial fraction stuff. So solution, we got to have s squared y of s minus s times 1 minus 0 plus y of s equals e to the negative 2 pi s plus e to the negative 4 pi s. I'm just taking Laplace of both sides, basically. So on the left, I can factor out y of s, and that'll leave s squared plus 1 on the left. And I'll move the s to the right-hand side, plus e to the negative 2 pi s plus e to the negative 4 pi s. and then divide everything by s squared plus 1, so y of s will be equal to s over s squared plus 1 plus 1 over s squared plus 1 e to the negative 2 pi s plus 1 over s squared plus 1 e to the negative 4 pi s. So that'll tell me y of s, or now I take the inverse transform to get y of t. Y of t will be equal to inverse Laplace of s over s squared plus 1 is cosine of t plus u of t minus 2 pi times sine of t minus 2 pi plus u of t minus 4 pi times sine of t minus 4 pi. But because sine and cosine are periodic of 2 pi, this term, sine of t minus 2 pi, is actually really just sine of t. Because it's 2 pi periodic, and same thing here, this is really just sine of t. So I don't have to write that minus 2 pi or minus 4 pi on those signs. So I could really say y of t is just cosine of t plus u of t minus 2 pi sine of t plus u of t minus 4 pi times sine of t. And that is our solution. Good stuff. One more for the day, and we'll call it. So this one's going to be a little more exciting, maybe. It has partial fraction decomp, so that's why it's a little more involved, but not too bad. Just gotta get those partial fractions down. All right, last one. I'll just start a new slide here. Example. Solve the IVP. And this initial value problem is y double prime minus 7y prime plus 6y equals e to the t plus delta t minus 2 plus delta of t minus 4, and y of 0 is 0, y prime of 0 is 0. So it's always nice when your initial conditions are 0 because you don't really have to subtract anything. So let's do it. S squared capital Y of S minus 0 minus 0 minus 7 S capital Y of S minus 0 plus 6 capital Y of S equals 1 over S minus 1 plus e to the negative 2s plus e to the negative 4s. So on the left we have capital Y of S times S squared minus 7s plus 6 equals 1 over S minus 1 plus e to the negative 2s plus e to the negative 4s. And then Y of S is equal to, let me factor this, let's factor this first before I solve for Y of S. So if we factor this S squared minus 7s plus 6, I think we can factor that as 6 and 1, so S minus 1, S minus 6. So let's do that. When we divide by that. So we get y of s, capital Y of s, is going to be 1 over s minus 1 squared times s minus 6 plus 1 over s minus 1 times s minus 6 e to the negative 2s plus 1 over s minus 1 s minus 6 e to the negative 4s. So really it's just two partial fraction decomps that we have to do. I'll just go ahead and tell you what the decomps are. So 1 over s minus 1 squared times s minus 6 turns out to be negative 1 over 25, 1 over s minus 1, minus 1 over 5, 1 over s minus 1 squared, plus 1 over 25, 1 over s minus 6. And the other one, 1 over s minus 1, s minus 6, that decomp turns out to be, I think both are 1/5. So 1 over 5, 1 over s minus 1, plus 1 over 5, 1 over s minus 6. So that's our two partial fraction decompositions. And so y of s can be written as negative 1 over 25, 1 over s minus 1, plus, minus 1 over 5, 1 over s minus 1 squared, plus 1 over 25, 1 over s minus 6, plus, parentheses, 1/5, 1 over s minus 1, plus 1/5, 1 over s minus 6, e to the negative 2s, plus 1/5, 1 over s minus 1, plus 1/5, 1 over s minus 6, e to the negative 4s. And now take the inverse transform. You get y of t is going to be negative 1 over 25 e to the t minus 1 over 5 t e to the t. So you could, it's like a first translation theorem in reverse. So that one's a little tricky. This is really first translation in reverse. First translation reverse. And then plus 1 over 25 e to the 6t plus, and then I'll put a u of t minus 2 out front, times 1/5 e to the t minus 2 plus 1/5 e to the 6 t minus 2 plus u of t minus 4 times 1/5 e to the t minus 4 plus 1/5 e to the 6 t minus 4. And that is our solution. So it was a little tricky there. We had that first translation theorem reverse, and then we also on the e to the negative 2s and e to negative 4s, that's going to be a second translation theorem in reverse to get those inverse transforms. But yeah, that's it. That's our last example for this section, 7.5 Dirac Delta functions. So just be super comfortable with your transforms and your inverse transforms and your first translation theorem and your second translation theorem going both ways. You need to be able to take the transform and take the inverse transform with both translation theorems. Also, convolution, periodic functions, transforms of derivatives, derivatives of transforms, and now Dirac Delta functions. That's it for Laplace transforms, at least what we're going to do with them. We could use Laplace transforms to talk about systems of differential equations, but we're not going to get that far. We're only going to be able to introduce systems of differential equations in Chapter 8 and talk about their different solutions based on the eigenvalues. But yeah, that's where we're going from here. So any questions before we call it a day? Any questions? All right, if no questions, smash that like button on the way out. See you guys next week. Have a good weekend. Hard to say. Review session. Maybe I'll try to schedule something on Zoom. I'll let you guys know through Discord or Moodle or whatever. But I'll let you know. We'll see. Yeah, the third exam is going to be 6.1 to 7.1. So series solutions and then using the definition of Laplace transform to calculate Laplace transform. That's right. The repeat problem is the spring mass problem. And we may or may not have you work out the whole thing, but some form of spring mass will show up on the third exam as a repeat.